Good afternoon everyone, I am Mr. Ish. Thank you for joining me in this video on prism volumes derived using integral calculus. We'll be looking at cubes, rectangular prisms, and we will look at triangular pyramids. It doesn't matter if that pyramid has a square base or rectangular base, the procedure is basically the same. In all these instances of these three examples we look at, these prism volume derivations, keep in mind we're not rotating a curve around an axis, because that type of rotational or dynamic movement leads to curved lines and circular cross sections. In these instances of these prisms, we have cross sections which have sharply defined angles, right angles and corners. Therefore, you cannot be looking at dynamic movement of curves about an axis. But like in any volume derivation, you're always looking at this specific fact. From a lower interval to an upper interval, you're looking at an area. We can just say a cross-sectional area of a slice that will be integrated over that limit with regards to dx or dy, but this right here is the basic premise. You take a cross-sectional area, you do a limit of sums for this specific area, and you integrate it across your interval, and you are essentially bringing a volume derivation with regards to that, an area being integrated across an interval. All these volume derivations that you'll see, the three of them, they're easy. Let's start with the cube. We know the volume of a cube is generally s cube or L cube, side times side times side, or length times length times length. We start here with a coordinate system and we draw a square. We use the designation S for side. We convert this into a three-dimensional object, a cube, having 6 faces, all of which are square. If you want to think of a cross-sectional area, the slice and the area of that slice, and you want to integrate it, you start by making a little cut. You make this little cut and you take this little square slice and you bring it out, and you know, since we're dealing with a cube, all of these have a dimension of s. The area of this must therefore be s times s, which is s squared. So now we know that we have a cross-sectional slice available for integration across an interval from origin 0 all the way up to this s comma 0, and the volume derivation is very easy. You're looking at something from 0 to s, the area of a cross-sectional slice being s squared with regards to dx. The s squared can come out as a constant, and you're looking at something which looks like this, dx. The hidden antiderivative x comes into play, and you have s to 0, upper lower limit. You bring in the upper limit and you multiply with s squared, and you have s cubed being the volume of a cube. And that's how you do it. You take a cross-sectional slice, you determine the area of that cross-section, you integrate that cross-section from a lower to upper limit, and it gives you your volume of that cube. The rectangular prism volume determination is not hard by any means. You know the volume of a rectangular prism is length times width times height. Again, you can start with a good xy plane. Draw a rectangle, make this into a prism, giving it three-dimensional qualities, and you don't have to do this. This right here is just for explanatory purposes. A dimension of length, a dimension here of height, and going across right here is a dimension of width. We know that to determine the volume, we have to take a cross-sectional slice, determine its area, and integrate it across our interval. We can easily bring a slice out of this, and we have something which looks like this. We know with regards to this slice, we're having a W going across and we're having a height. This slice is really a square, but it's just drawn in this way simply because of the angle by which we're viewing this object. Here, the area of this slice is just h times w, or length times width. You can just say hw. So we know that a slice of this hw, having the area of hw, has to be integrated from this interval 0 up to this interval L comma 0. We have this little slice which exists right in here, and we integrate it across this interval. hw gets integrated. So what's our volume formula here? It's not hard. We're going from a 0 lower limit to L upper limit, an area of a slice being integrated, which is my a of x, with regards to dx. This hw, height times width, can come out as a constant, and we have a dx. Here we bring an hw along with this x, the hidden antiderivative, which comes out from this integral procedure, L to 0. When we do the upper limit, the lower limit, we get length times width times height, and that gives us the volume of this rectangular prism, which is what we wanted all along. Again, no different than the previous example. A cross-sectional slice is plucked out, it's visualized, the area of the slice is determined, and then that area is integrated from a lower limit to your upper limit L, and that's it. The volume of a square pyramid formula determination is slightly tricky. because there are a few nuances that have to be kept in mind. Anyhow, the formula is 1 over 3 times height times length, especially for a square pyramid having a square where all sides are equal. But if you're looking at a rectangular pyramid, rectangular base pyramid, you know this L square can be substituted for L and W. 1 over 3 H L W, height times length times width times 1 over 3 for a pyramid having a rectangular base. But we're looking here at a square pyramid, and the procedure for rectangular pyramid base is exactly the same. You cannot do, in this instance, a slice, which you can easily draw, but you cannot just pull out this slice and then look at it this way and then just say, assuming sides of s and s, and then we say s square, and we integrate this s square across our interval, whether it be from 0 to whatever higher limit, because that procedure is wrong, because as you can see, this shape narrows or it converges towards its apex. If you just integrate this across your interval from your lower limit up to your upper limit, you're not seeing that convergence come into play, and then this procedure is no different than you looking at the volume determination of a rectangular prism or a cube. We have to somehow account for this convergence of this shape, because these squares that you can slice out will be large at the base, but towards the apex they become minutely small, and you have to account for that. And how do you do that? It's by means of you visualizing this triangle. It could be an isosceles or an equilateral, and you have to bring in a certain ratio into play. If this slice over here represents this line over here, then you have this triangular face, or you can even say a triangular cross section. You have to come up with a ratio. The ratio is such, you can identify this as your side, S for side, this is my side of interest, and my L over here, or you can even use B for base. From this distance of the apex to this side, I have a certain height of X. From the apex of this pyramid down to its base, I have a certain height of this pyramid, and it's called H. By using the properties of similar triangles, especially when we're talking about equilateral and isosceles, where you have similarities in these two triangles which are generated. Here's my small triangle and my large triangle, they're similar triangles. By using the properties of similar triangles, you can come up with the following ratio. This height distance divided by its corresponding side is equal to this total height divided by its corresponding side, L. You're solving here for S. S is equal to Lx over H. Now, if you come back to this image right here, you take this cross-sectional slice and you pluck it out. And we've drawn it out like we see it here. Now, each of these S's here is well represented by this formula here, which very well accounts for the convergence of this triangle as you go from the base to the apex, the convergence of these slices towards that apex. Now, in each of these instances, the area of this shape is S times S, but it's really Lx over H times Lx over H, and that's L square x square over H square. And now this right here represents the cross-sectional area of this slice, which must be integrated from your lower limit to upper limit. And how do we determine that limit? Take this and rotate it horizontally. You can rotate the pyramid horizontally, and you can have an entire height over here of your pyramid. From base to apex you have a height. You can go from 0 to H, and this 0 to H represents our interval over which this cross-sectional slice area is integrated, and that gives us our volume. So let's take this to completion. Volume with regards to X for this square pyramid is equal to, you have this interval 0 to H right over here, this L square x square over H square dx. You have to integrate with respect to X. You have L square x cube over 3H square, upper limit H to 0. Plug in the H's and the zeros are meaningless. You have L square H cube over 3H square. You simplify this. H square cancels out with two of those H's, H square, and you're left with L square H over 3. Which, as you can say, is length times height over 3 for a square pyramid. But if you're talking about a rectangular pyramid, you can substitute one length for a width, because then you would have a length and a width in that base, and you'd have length times width times height divided by 3 to be the volume here of a pyramid with a rectangular base, and the volume here for a pyramid with a square base, and that's it. The volume is derived. So keep in mind there's no rotation involved here, no dynamic movement of a curve about an axis, because in that instance you'll be getting cross-sectional slices, but we're not dealing with those type of shapes like cylinders, cones, or spheres or hemispheres. We're looking here at prisms which have sharply defined line angles and right triangles in terms of their slices. So this is the procedure we use. We take a slice, we pluck it out, determine its area for that cross-sectional slice, and we integrate over our interval, and that gives you your volume. And that's it. The cube, the rectangular prism, and the square pyramid volumes are all shown and demonstrated here for you. Thank you for watching. Have a nice day.